Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System. And we're up to Lecture 30, where we begin our tour of the solar system with the planet Mercury. So let's just start with some basic facts about Mercury. Don't worry about memorizing these. If you need any of them on a quiz, I will provide them, but I just want to lay the groundwork so that we have some basic numbers in our head. First of all, Mercury is 0.39 astronomical units from the Sun, so a little bit less than 0.4 astronomical units, or about 40% of the distance from the Earth to the Sun. It takes Mercury just a little bit less than 88 days to orbit the Sun one time, which is a little bit less than 3 months. So in one of our years, Mercury orbits the Sun more than 4 times. Its orbit is inclined by about 7 degrees with respect to the Earth's orbit around the Sun. That is, it's inclined or tilted by about 7 degrees with respect to the ecliptic, and that gives us the highest inclination of any of the planets in the solar system, other than Pluto, if you consider Pluto a planet. It also has the highest eccentricity other than Pluto. Its orbital eccentricity is 0.206. And so that means that Mercury has quite an elliptical orbit compared to most of the other planets. Its diameter is about 38% the diameter of the Earth, and its mass is about 0.055 times the mass of the Earth, or a little bit more than about 1/20th the mass of the Earth. Its density is almost the density that the Earth has, 5.43 grams per cubic centimeter, which means, of course, as we already knew, that Mercury is a terrestrial, rocky planet. As we'll find out, Mercury also has a giant iron-nickel core inside of it. And its rotation period is about 58.6 days. So to rotate on its axis one time takes Mercury 58.6 days. Now, it's not obvious from these two numbers, but the rotation period and the orbital period, as we will see here in a few minutes, actually are related to one another. So first of all, what can we say about Mercury from Earth? Mercury is always close to the Sun in the sky because Mercury is orbiting in our solar system closer to the Sun than we are. You can generally see Mercury in the early evening right after the sun sets, or in the early morning right before the sun rises, but Mercury never gets very far from the Sun. It's never out in the middle of the night, and when we can see it in the evening or morning sky, it's always very low in the sky. Mercury is also fairly small. And for those reasons, we can't really see any surface features on Mercury from Earth. Now, you will recall that Venus goes through phases because it is closer to the Sun than the Earth is, and Mercury does the same. Mercury goes through a full set of phases as seen from the Earth because it is closer to the Sun than we are. So here's Mercury in the half phase. If it was the Moon, we would call it the quarter phase. So that's Mercury, and that's a pretty decent ground-based photograph of Mercury. Doesn't show you any surface features. You really can't make out any details on the planet. Most of what we know about the details on Mercury, like this patched together photograph that you see in the background, come from spacecraft. And we'll talk more about those spacecraft here in a second. Okay, so since Mercury is closer to the Sun than we are, it goes through phases. Ground-based telescopes don't really show any surface features. Up until 2007, only one spacecraft had ever visited Mercury, and it flew by Mercury 3 times. And that was the Mariner 10 spacecraft. And it made 3 flybys in 1974 and 1975. But interestingly, every time it flew by, it saw the same face of Mercury. So ultimately, only about 45% of the planet had been mapped. So this is Mercury as a whole, and this is the small part of the planet that had been mapped. They discovered half of this giant impact basin called the Caloris Basin. So you can see the Caloris Basin sitting right here, just like the giant impact basins on the Moon. But in this case, we could only see half of it, but the other half wasn't photographed because it was in darkness. So that was the half of Mercury that was in darkness. This was the half of Mercury that was below the horizon as seen by that spacecraft. So I think here's a great example of how much work there is still to do in our solar system. Now, we have since mapped the rest of Mercury. We're going to see here in a few minutes that the Messenger spacecraft passed by Mercury 3 times and then went into orbit around Mercury and has fully mapped the planet. But that said, That didn't happen until the 21st century. And so there's still lots to be done in our solar system. Okay. Compared to the other terrestrial planets, Mercury has an outsized, an oversized, I guess I should say, giant iron nickel core. So its iron nickel core is about 65% of the mass of the planet. And it's an interesting question as to why Mercury was born with such a large core. Like the Earth, it has a solid inner core. We believe it has a molten core. We'll see the evidence for that here in a second. But the core is quite big compared to the rest of the planet. The two hypotheses that have been put forth to explain this is it is possible that Mercury once had a much thicker mantle, but in the late heavy bombardment in the early history of the solar system, possibly Mercury was bombarded, collided with so many things that much of that mantle was blown off the planet. Or it's possible that Mercury, being so close to the sun, was just made of more metals than rock. So it could be that it was born this way, that it was created this way, or it could be that impacts in the early history blew off some of its mantle. The reason that we believe Mercury has a molten, at least a partly molten core, is that it has a magnetic field. And that magnetic field is about 0.5% of the strength of the Earth's magnetic field. So it's much weaker than the Earth's magnetic field. But that's not too surprising. Mercury is much smaller than the Earth and it rotates much slower. So it's not surprising that it has a weaker field. What is surprising is that it has a field at all. Mercury is so small that it should have cooled off a long time ago in our solar system. You'll remember that smaller bodies cool off faster, but somehow Mercury has managed to retain a molten layer in its core, and that molten metal layer is generating a magnetic field. What we believe today from the MESSENGER mission is what's preventing this core from freezing is the presence of sulfur. Large amounts of sulfur in the core, iron sulfide, has a higher freezing point than pure iron or pure iron nickel. And it might be that contaminant, that sulfur in the iron, that has allowed that outer core to stay molten. Mercury, like our moon, is an airless world. It has no atmosphere at all. Sometimes you will read that when particles hit the surface of Mercury, when tiny meteors or meteorites hit the surface of Mercury, they can vaporize some of the rocks, and that vapor can hang around for a short period of time. So sometimes you'll read that Mercury has a very, very, very thin atmosphere. But just keep in mind that's mostly just vaporized gases from objects colliding with the surface of Mercury. I would argue that for all intents and purposes, like our moon, Mercury has no atmosphere. It is a vacuum world. And like our moon, it is covered in impact craters for the same reason that our moon is covered in impact craters. With no atmosphere, there is no erosion on Mercury. And those craters can last a very long time. And just as our moon has craters, and just as our moon has impact basins, Mercury has impact basins as well. And one of these is known as the Caloris Basin. We will see in a minute how it gets its name. It's that part of Mercury that is facing towards the sun when Mercury is at its closest to the sun. So the Caloris Basin sees some of the hottest temperatures on Mercury. Now, the Caloris Basin is a giant impact basin, and exactly 180 degrees away from the Caloris Basin, on the opposite side of Mercury, is this highly jumbled terrain. Now, don't look at the impact craters here, but look at the stuff in between the impact craters, and you see a terrain that is very, very broken apart and very jumbled. And one of the ideas as to where this jumbled terrain came from is that it came from seismic waves. When the Caloris impact happened and made the Caloris Basin on Mercury, as those seismic waves traveled through the planet, they were focused on the opposite side of the planet and pushed up all this chaotic terrain, as it's sometimes called, or jumbled terrain on the far side of Mercury. Mercury also has scarps. These scarps are evidence that Mercury has cooled off over time and that the surface of Mercury has actually shrunk a little bit. And this scarp, called Discovery Scarp, so you can see the scarp running across the middle of the field of view here. So it is a place where the rocks have broken and they have slid on top of one another. You'll notice that crater there up at the top that's 35 kilometers in diameter. We can actually tell just from looking at this photograph which came first, the crater or the scarp. So go ahead and go out there to Learning Catalytics and answer this question. Which is older, Discovery Scarp or the two labeled craters A and B? So use stratigraphy, the study of layers that we talked about in the last lecture, and take a look at these two craters and see if you can figure out whether they came before the scarp or after the scarp. So answer the question, which is older? All right, welcome back. What did you come up with for this one? Well, I would argue, let me go back to this picture because we can see it in a bit more detail. I would argue that since the scarp is cutting across the craters, that the craters had to be there first and the scarp came second. Because think about what would have happened if the scarp was there first. If the scarp was there first, when this impact happened and blew this crater on Mercury, it would have erased evidence of the scarp there. When this impact happened, it would have erased evidence of that scarp as well. So it must be that the craters were there first and the scarp happened later. So the order in which those happened was the craters first and the scarp second. As I mentioned, those scarps are the result of Mercury's surface cooling. Like many things, when they cool off, they contract. So as Mercury has cooled off over time, the planet has shrunk. The problem with the planet shrinking is that means that there's no place for the surface to go. If you imagine taking an apple or an orange and shrinking the inside of it, the outside of the orange is going to have to crack and little parts of it are going to have to overlap one another. And so that is what has happened on Mercury. These scarps are a result of the shrinking of the planet. And the best estimate that we have is that Mercury has shrunk by about 7 kilometers over its lifetime as it has cooled off. Now, because it is so close to the sun, Mercury is extremely hot. During the daytime, the surface temperature can exceed 700 Kelvin, which is about 800 degrees Fahrenheit. And it's typically about 600 Kelvin, which is 620 degrees Fahrenheit. Since it has no atmosphere, at night, the planet doesn't retain any of that heat and it cools off all the way down to around 90 degrees Kelvin, which is minus 300 Fahrenheit. So look at those numbers. In the daytime, at its hottest, the surface can be 800 Fahrenheit. And in the middle of the night, it can be minus 300 Fahrenheit, a total swing of 1,100 degrees in temperature. That means Mercury has the greatest change in temperature between day and night of any planet in the solar system. And that's again because there's no atmosphere. Remember, the greenhouse effect traps heat down on the surface. Well, if you have no atmosphere, there's nothing to trap that heat, and the surface radiates all its heat away. So it gets quite cold at night. But of course, with the bright sun shining on it, and since Mercury is so close to the sun, it's quite hot during the daytime. Now, in an earlier lecture, we talked about tidal locking. We mentioned that the moon is tidally locked to the Earth. That is, the moon always keeps the same face towards the Earth. We talked about some of the moons of Jupiter are tidally locked to Jupiter. They always keep the same face towards Jupiter. Mercury has an interesting tidal interaction between its rotation and its revolution around the sun, related to the gravity of the sun. The tidal forces from the sun have locked Mercury, but it's not locked so that one face keeps towards the sun. Mercury rotates on its axis exactly 3 times for every 2 times that it orbits the sun. So let's take a look at what we mean by that. So let's start down here at the bottom at position 1, and let's imagine that this blue dot up here, turns out that is the Caloris Basin on Mercury, the Caloris Basin, which is facing towards the sun, where Mercury is closest to the sun in its elliptical orbit around the sun. So it is right now noon at Caloris Basin. As Mercury orbits around the sun, Mercury also turns. It turns in a prograde fashion. So remember, as seen from above, everything in the all the planets in the solar system orbit counterclockwise. Most of the planets spin counterclockwise. As we tour through the planets, we'll see the exceptions, but Mercury is not one of them. Mercury spins counterclockwise. So here's where Caloris Basin starts. As Mercury spins, it ends up there, ends up down here, ends up over here, ends up over there, ends up over there, and then by position 7, it ends down here. And now because we're starting the second orbit, the color of it changed from blue to red. So now it's here, it's there, it's there, it's there, it's there, it's there, and now it's back. And this was just 15 arbitrary steps there to show you that it's back. So after Mercury goes around once, twice, the planet actually completes 3 full rotations. So let's watch the Caloris Basin here. So here it is facing towards the top of the screen. So we have, it turns, it completes its first rotation right there. You'll notice the Caloris Basin is facing towards the top of the screen again. And then it keeps turning, and then here we go to 7, turning, and here it's now facing towards the top of the screen again. So it's completed its second rotation. And then it goes through these to get down to here where it completes its third rotation. So it spins on its axis exactly 3 times for every 2 orbits. So that raises an interesting question. Does an astronaut standing on the surface of does an astronaut standing on the surface of Mercury ever see the sun rise or set? True or false? An astronaut standing on the surface of Mercury would never see the sun rise or set. So take a look at those rotations, take a look at that diagram, and answer this question in Learning Catalytics. Would an astronaut standing on the surface of Mercury see the sun rise and set? All right, what did you come up with for this one? Well, to figure out the answer, let's go ahead and put an astronaut on the surface of Mercury. And let's imagine that that astronaut is standing in the middle of the Caloris Basin. And what we want to do is we need to find out if the sun's ever going to rise and set. We need to follow this astronaut on the Caloris Basin and see when the sun rises and sets, if it ever does. So our astronaut is standing straight up and down here, but most importantly, it is noon for the astronaut right there. So it is noon. All right. Mercury rotates, noon is over here, so now it's like 1 o'clock in the afternoon, a little bit after noon. Over here, we see that it is now noon is over here, so we see that this is about 3 o'clock in the afternoon. But you'll notice that right here, the astronaut is right on the edge of Mercury. The sun would be setting for that astronaut. Here they've rotated to the side of Mercury facing away from the sun. Here they're facing away from the sun. Here they're facing away from the sun. Still facing away from the sun, still facing away from the sun. So this is the nighttime, still facing away from the sun, and the sun rises right about, it's somewhere between 11 and 12. The sun will rise again. They're right on the edge of Mercury. Now in 13, they're on the daytime side, 14, they're on the daytime side, and at 15, they return to noon. So here's the fascinating thing about Mercury. This is noon. You'll notice that as we went all the way around, we never encountered another noon until we had finished 2 complete revolutions around the sun. That is, a full day on Mercury is 2 Mercury years. But an astronaut would see the sun rise and set, but they get 1 sunrise every 2 years, and they get 1 sunset every 2 years, 2 Mercury years, that is, on Mercury. Okay. Other interesting things about Mercury. Radar observations done by giant radio telescopes here on the surface of the Earth, in particular this one called Arecibo Radio Observatory. It's down in Puerto Rico, in northern Puerto Rico. There are very powerful radio transmitters here that can send radio waves off into space. They bounce off the moon. They've bounced radar waves off Venus. They have bounced them off Mercury. They have bounced them off some of the outer moons of the solar system. So we've done a lot of radar work in astronomy where we can actually send radio signals out, bounce them off, and come back. Not all radio telescopes are used in that way. Some radio telescopes, many of them actually are just passive listeners. But in this case, they have an actual transmitter here, a radio transmitter that can send radar waves into space. So that is Arecibo Observatory. They have sent radio waves to Mercury and bounced the radio waves off the surface, and we can actually use that to map the surface of Mercury. And it turns out that at the South Pole, deep down at the pole on Mercury, there are craters that are so deep that the sun never shines deep down in those craters, and ice might actually exist there. Yes, ice can exist on Mercury. This is a very crude radar image of Mercury, and you can notice this high reflectivity up here at the pole. Sorry, it's at the North Pole. So you can see this very high reflectivity up here at the North Pole. With more sophisticated radar imaging, so this was a radar image that was done with Arecibo Observatory. With this radar image, you can actually see these craters at the North Pole. And down at the bottom of the craters, there's this very reflective material. And that very reflective material could very well be ice. Those craters could be so deep that because it's at the pole, the sunlight is coming from the side. And since the sunlight is coming from the side and the crater is so deep, the sunlight never shines on the bottom of the crater. And so, like the night side of Mercury, since the sun never shines on it, it can get quite cold. Down at the bottoms of these craters. So if a comet or an asteroid strikes Mercury and some of that water vapor is released, that water vapor will settle in these craters. It turns out we have seen exactly the same thing here on our moon. Our moon, especially the south pole of our moon, has craters that are so deep that they may have ice down in the bottoms of them. Now, I mentioned that most of what we know from Mercury comes from spacecraft. In addition to that Mariner 10 spacecraft in 1974 and 1975, Mercury was visited by the Messenger spacecraft. Messenger was launched on August 3rd, 2004 on a Delta II rocket from Cape Canaveral Air Force Station in Florida. And Messenger is an acronym. The scientists who devised this mission to go to Mercury knew that, of course, Mercury was the winged god. Mercury is the messenger, so they really wanted to call the spacecraft Messenger. And NASA has a history of using acronyms for things. And so Messenger actually stands for the Mercury Surface, Space, Environment, Geochemistry, and Ranging Mission. I think it is one of the most tortured acronyms that NASA has ever come up with. But it was the first mission to Mercury since Mariner 10 in 74 and 75, and really the only other mission. We'll see here in a minute that there's still one on the way. It used, in order to get to Mercury, it had to go on a very long orbit. You'll notice that it was launched in August of 2004, but it didn't actually get into orbit around Mercury until 2011. It took 7 years to get to Mercury. Now, that's really quite remarkable given how close Mercury is to the Earth. I mean, we're 1 astronomical unit from the sun. Mercury's 0.4 astronomical units from the sun, so it's only a little more than half an astronomical unit away from us. It's basically the same distance away from us that Mars is. And a voyage from Earth to Mars only takes 6 months. So you might wonder, why is it that the voyage from Earth to Mercury took 7 years? And the answer is, it's very hard to fall into the inner solar system. You might remember the circular orbit velocity equation. As the Earth orbits the sun, in order to fall into the sun, we have to lose a tremendous amount of energy. And it turns out the United States does not have any rockets in our inventory that are powerful enough to send Messenger directly to Mercury. What we had to do instead was, when it was launched, we put it into an elliptical orbit. It went around the sun once, and a year after launch, so it was launched in August of 2004, a year after launch in August of 2005, it had a close encounter with the Earth. And the Earth's gravity bent the orbit of the spacecraft so that now it went to the inner solar system. And it orbited around the inner solar system a couple times, and then in October of 2006, it flew by Venus. It used the gravity of Venus to change its orbit. It had another flyby of Venus in June of 2007, and then it had 3 flybys of Mercury. Each of these flybys was designed so that the spacecraft would give up a little bit of its energy to the planet. That is, the planet would slow the spacecraft down, which would allow it to fall into the inner solar system. And that's one of the ironies of spaceflight. And if you're interested in learning more about this, we talk a lot about orbits in my Astronomy 3450 Mission to Mars class. But to fall to the inner solar system, you have to slow down. That is, if you're on Earth here and you speed yourself up, you will move to the outer solar system. But if you slow yourself down, you'll fall in. But here's the ironic thing. As you fall in, you gain energy from falling in and you speed up. So all these encounters were designed to bleed energy, to bleed speed from the spacecraft, to allow it to fall in, till finally in March of 2011, it was flying slowly enough that it could encounter Mercury and go into orbit. So it entered orbit around Mercury in 2011. Now, Mercury's a difficult place to work. You're less than 0.4 astronomical units from the sun. So the spacecraft had to protect itself from the sun. And in fact, the spacecraft had a giant heat shield right here. This heat shield was made of Kevlar, the same material that bulletproof vests are made of. And the spacecraft itself was hiding behind that heat shield. And that heat shield kept the heat of the sun off the sensitive scientific instruments and the electronics, the computers, everything that was used to run the spacecraft. In fact, the only thing sticking out from behind the heat shield were the two solar arrays, and they were specifically designed to survive under high temperatures. Another problem that Messenger faced is that as it flew over the surface of Mercury and flew low over the surface of Mercury, Mercury itself was really hot. And as all that heat radiates off the surface of Mercury, it too would heat up the spacecraft. So the spacecraft was put into a highly elliptical orbit, which means that the spacecraft would fly very close to Mercury, take all of its photographs, do all of its work on Mercury, and then it would fly for a long period of time far from Mercury that allowed it to cool off before falling back down and doing it again. And then it would come back out and spend a long time out here. Over the lifetime of the mission, the orbit was about a 12-hour orbit. So it would orbit Mercury about every 12 hours. So these are some numbers from August of 2014, so a little bit before the end of the mission, about the Messenger spacecraft in orbit around Mercury. So it returned 10 terabytes of data. It came as close as 60 miles to the surface of Mercury. It made 3,308 orbits by August 1st, 2014, and the mission continued for another, let's see, what would it be? Another 8 months or so after that. Made 29 trips around the sun in orbit around Mercury. So this is what the spacecraft looked like. So here is the sunshade, or that sun shield that protected it from the brightness of the sun, the solar array sticking out, and then all the equipment in the spacecraft, a thruster that was used for maneuvering the spacecraft, the computers, the electronics that were used, the antenna here and another antenna here that were used to communicate with Earth, this adapter down here that fit the spacecraft on top of the launch vehicle, and inside that adapter was where looking downward, was where all the scientific instruments were located. To give you some scale, that's what the sun shield looks like. The sunshade looked like before launch. So here is a technician working on the spacecraft just before launch, examining the sun shield and getting it into place. Spacecraft like this are packed with scientific instruments to study the planet. So, for example, there was a laser altimeter that would send a laser light down to the surface that would bounce off the surface and come back. How long it took the laser to go down, bounce off, and come back could tell us the height of the surface features on Mercury, because we know where the spacecraft is right well. There was a gamma ray spectrometer that measured gamma rays that come off the surface of Mercury. These gamma rays are the result of particles impacting the surface of high energy particles impacting the surface of Mercury and giving off gamma rays. There was an atmospheric and surface composition spectrometer. This was a device that breaks light into its component colors in order to see what the surface of Mercury was made of, and Mercury's very thin atmosphere that I had mentioned earlier, what it was composed of. There was an X-ray spectrometer to look at X-rays being released from the surface. There was an imaging system that allowed us to take high-resolution pictures of the surface of Mercury. Another X-ray spectrometer, a data processing unit, a neutron spectrometer, energetic particle detector, a magnetometer to study Mercury's magnetic field. So you can see packed inside the spacecraft are all these different scientific instruments built by scientists literally around the world that were mounted on the spacecraft. So when you think of a spacecraft going and visiting a planet like Mercury, don't think about it just bringing cameras to take close-up photographs. Yes, cameras are a part of it, but there are lots of other instruments on board as well. Now, one of the things that they did with these cameras is they could take spectral images of Mercury, or multispectral images as they're sometimes called. These are images that use color filters to isolate specific colors that are associated with specific minerals. So not only can you map the planet and see what the planet looks like, but you can also determine the mineralogical composition of the different areas on Mercury's surface. Like the moon, Mercury is not only covered in craters and impact basins, but there is clearly evidence for volcanic activity, lava flows on the surface of Mercury as well. So just as an example of an up-close image, this is an up-close image of a crater on the surface of Mercury and this really, really interesting cracked pattern here that still to this day is not well understood. It looks like a place where something underneath the surface welled up, and as the surface welled up, it would have that little bit of the surface would have tried to expand, and as it expanded, it cracked and left all these fossae, as they're called, all these cracks on the surface. An interesting question is whether these cracks are related to the crater or not. The indication that they're probably not related to the crater is, first of all, and I should have done this as a learning catalytics question, maybe next year, which came first, the fossae or the crater? And go ahead and answer that question. I don't have learning catalytics, so don't go out to learning catalytics on this one, but just answer the question in your head. Which came first? Did they happen at the same time? Did the crater come first, or did the cracks come first? All right, what do you think on this one? Well, we can see lots of cracks, and we notice that some of the cracks come right up to the rim of the crater, but you'll notice that they don't seem to hurt or cut the rim of the crater. I believe that this means that the crater came second. The cracks were there and the crater came later on. I think other good evidence for that is right here. You can see the ejecta blanket from the crater has actually filled in some of these cracks. I think the ejecta blanket from the crater here has filled in some of those cracks right there. And so the crater came later than the cracks, and it's probably not related. It's probably just a coincidence that it landed right on top of them. You'll also notice that it's not quite centered. There's a clear center to this cracking, and the crater is pretty far off center. Maybe they're related, but it certainly appears as if the crater came later. Now, I talked earlier about the possibility of ice in the poles and the North Pole of Mercury, and in November of 2012, the Messenger science team announced additional evidence for ice on Mercury. The gamma ray spectrometer, which measures those gamma rays released by the surface, and a neutron spectrometer, which measures neutrons released off the surface. The neutrons are actually blasted off the surface by cosmic rays. Cosmic rays are high energy particles. Most of them come from deep space. But these cosmic rays would hit the surface and they would blast neutrons off the surface. But as they passed over the poles, they found that the neutron flux dropped. And one of the reasons that neutrons would drop is that hydrogen is an excellent absorber of neutrons. And so that indicates the presence of hydrogen deep down inside these craters at the poles. And well, hydrogen is likely to exist in the form of water. So this was yet additional evidence for ice in the poles. Messenger also measured the infrared reflectivity at the poles and found it was consistent at water ice. Here's one of the craters at the pole that's continually shadowed because the sunlight's coming in at such a high angle here. Remember, this is at the pole of Mercury, and the pole of Mercury never points at the sun. So if the crater is deep enough, well, we'll use the North Pole here. If the crater is deep enough, the sunlight never gets down to the bottom. However, sunlight does reach the rim of the crater, and some of that sunlight was scattered down to the bottom. And they could use that to photograph the bottoms of the craters, and they found that it was consistent with water ice. The temperatures and the models of the bottoms of those craters were consistent with the presence of water ice as well. Now, we don't know how thick this ice is. It could be anywhere between half a meter thick and even up to 20 meters thick. But the team estimated that there was somewhere between 100 billion and 1 trillion tons of ice deep down in these craters at the pole of Mercury. As I mentioned earlier, our moon also has ice in deep down inside of craters at its south pole, and that will likely be the next landing areas where humans land on the surface of the moon. Will be down near the south pole, near these areas with ice, because this ice can both be converted into drinking water for the astronauts, but can also, with electricity, be broken into hydrogen and oxygen, which is a very efficient rocket fuel. And so that ice will provide a way to sustain life on the moon, on a colony, and will also provide rocket fuel. All right. Well, how about the end of the mission? Well, the Messenger mission was originally designed to last 1 Earth year, March 2011 to March 2012. But at the end of March 2012, the spacecraft was working just fine. It had lots of fuel on board. And as very often happens at NASA, missions are designed for a specific amount of time. You design the mission to last what's called the nominal mission. But you hope it'll last longer than that, and you hope that NASA will continue to fund the mission beyond that nominal mission. And in this case, the nominal mission was 1 year, but at the end of that first year, everything was going great. NASA funded them for a second year, so it was extended once, and it operated from March 2012 to March 2013. It was still operating well, and so it was extended again from March 2013 to April 2015. So they got 2 extensions on the mission. However, ultimately, the mission was going to come to an end because the spacecraft had to use its maneuvering fuel to turn itself, to point its antenna back towards Earth, to send its data to Earth. And every time it did that, it used a little bit of its maneuvering fuel. And in late 2014, Messenger had used up all of its maneuvering fuel, and the spacecraft ultimately crashed to the surface on April 30th, 2015 at a speed of 8,750 miles an hour, about 14,000 kilometers per hour. So that was the end of the Messenger mission. Scientists are still analyzing the data that came out of the Messenger mission. We will likely be analyzing that data for another decade to come. But that doesn't end the exploration of Mercury. Right now, in transit to Mercury is a European Space Agency mission called Bepi Colombo. Bepi Colombo is named for an Italian scientist whose name was Giuseppe Bepi Colombo. That Italian scientist proposed using gravity maneuvers where you fly by another planet and use the gravity of that planet to modify your orbit to speed up or slow down. It was used as part of the Messenger 10 mission to get to Mercury. The Bepi Colombo mission consists of 2 spacecraft. Right now they're joined together, but when they get into orbit around Mercury, the 2 spacecraft will separate. One of them is the Mercury Planetary Orbiter, and it has very much the same kind of scientific instruments that the Messenger mission had. Only in this case, the spacecraft was launched in 2018, and so these instruments are more sophisticated than the ones that were launched on Messenger, simply because the spacecraft came a decade later, and there's been a lot of progress, both in technology and understanding of Mercury since then. So this is the planetary orbiter, and then the other spacecraft is a magnetospheric orbiter. It's got these long booms that will be used to measure very sensitively Mercury's magnetic field. And the reason we're interested in Mercury's magnetic field is because it's generated deep down inside the core of the planet. So right now, there are no plans. I really would argue there's not much hope for putting a lander down on the surface because Mercury is so hot. Originally, the Bepi Colombo mission was supposed to include some kind of a lander, but for budget reasons, it had to be eliminated from the mission. Maybe your generation will land a seismometer on the surface of Mercury so that we can get more accurate measurements of what the interior looks like. But for now, the best we'll be able to do is with the Mercury Magnetospheric Orbiter, measuring the magnetic field of Mercury, which is generated in the core. And that will tell us something about the interior structure of a planet that has an enormous iron-nickel core. As I said earlier, compared to all the other planets, all the other terrestrial planets, its iron-nickel core is larger relative to the planet than any other core of the terrestrial planets. So that is our quick tour of Mercury. Join me in the next lecture when we will take a look at the planet Venus.